So in class, we took a look at Kirchhoff's rules and what those were. Remember, there were two, the junction and the loop, right? Both of them had to deal with how you were adding certain quantities. For a junction, you're looking at the fact that the sum of my currents into a cluster of three or more wires was equal to, coming in was equal to the current coming out. The loop is looking at the potential differences. So the sum of all the potential differences in a closed loop is equal to 0. So we're going to end up applying those two rules to find all of our missing pieces. We're going to do that to find specifically A through C, and then we'll be able to find D and E based on that information. So let's start first by labeling some pieces that we have. I'm going to call this my V1. I'm going to call this V2. I am then going to label this R2, and this is going to be R3. You might be wondering why I'm doing these particular numbers. It's going to go with what's going on with my current. So I'm going to have current through this leg of my circuit. I'm going to have current through this leg of my circuit. And because this is one leg, you have to go through either of these items to get to any other part of the circuit, the current here is going to be the same for both. And then I have current going through here. So I have numbered these and named these in a way that allowed me to differentiate. The next thing we're going to look at is where do we predict our current to be flowing through this circuit. We typically see that current should be flowing from the positive terminal of our battery around the circuit to our negative terminal. As a result, because my long side is my positive and my short side is my negative, I'm predicting that current is going to flow like this for that side of my circuit. And I'm going to make a similar prediction for the other side, from my positive and into my negative. Because I'm seeing current flowing out of this particular spot here and flowing into this particular spot here, I know it has to go somewhere, and it has to go in one particular direction, and that's going to be down through this wire. Right? So I can actually label sort of a little bit what that's going to look like, and that if I labeled that, I'm looking at the fact that this piece here is going to be I3. This piece that's going to go around here, this is going to be I1, and this piece around here is going to be I2, and that's based on which pieces I actually have in my circuit. So those are the pieces that I'm looking at. The next thing I'm going to look at is actually picking my junctions. Well, where there are three or more wires combining are going to be junctions. This is junction A, and this is junction B. Right? And then, one last thing we get to pick is what are our loops going to be. So we get to pick how we're looking at loops, as long as it is one closed loop and we come back to where we start. So let's go ahead and do one loop. It's going to be go clockwise here, and one loop clockwise here. All right, it's going to go, so we're looking specifically at this shape for A, loop A, and this shape for loop B. So now we are ready to go ahead and get started with our problem solving. I'm going to go ahead and apply the junction rule first. Because we only have three unknowns and we're going to end up looking at two loops, we only need one junction rule. I'm going to go ahead and pick junction A. Right. As I do that, I see I have current 1 and current 2 coming in and current 3 coming out. So I1 plus I2 is equal to I3. So, and we only need to do one of our junctions because you'll notice that junction B ends up producing the same equation because my current in is I3 and my current out is I1 and I2. So now we're ready to go ahead and start applying the loop rule. So we're going to start with loop A. Right? And when we look at loop A, I'm going to go ahead and start with my battery and then go around. When I start from my battery, if I'm going from my negative terminal to my positive terminal, then I'm looking at the fact that this is a positive voltage. So I'm looking at positive V1, and I go through and then go through this resistor. I am going with the current, so this is negative IR. So this is negative I3 R3, and then there's nothing else in this particular loop, so I'm going to go ahead and just go ahead so that it is equal to 0. From here, I'm now able to then go to loop B. Loop B. And I can start at any particular point in this circuit. I'm going to go ahead and start with this one. And notice that if I go in the direction that's listed for this particular piece, I'm going to be going opposite my current. So now I'm doing plus I3 R3. And I go around, and now I'm going to go from my positive terminal to my negative terminal. So now I'm doing minus V2. And again, against my current is plus R2 I2. And that all, when I close again, my circuit is equal to 0. So now I have 3 equations for my 3 unknown pieces. I'm looking, remember, for the current through this piece, the current through this piece, and the current through this piece. So we got to take a look at what do we know and what do we not know to be able to solve anything. So we know the voltage of 1. We know the values of both of my resistors. We're only missing our currents. Well, I have voltage of 1, the value of my resistor. I'm looking for current 3. Well, we can go ahead and solve that equation for that particular variable. And when I do that, I get V1 is equal to I3 R3, or I3 is equal to V1 divided by R3. And when I plug those particular numbers in, I get the 1.5 volts divided by 100 ohms, which gives me 0.015 amps. So I've got ahead and solve for that one. So the current going through my 100 ohm resistor is 0.015 amps. So we have one more piece of information. Well, we know I3, we know R3, we know V2, we know R2. The only thing we're missing is I2. That means that we can go ahead and arrange that equation for that particular piece. When I do that, I get R2 I2 is equal to V2 minus I3 R3, or I2 is equal to all this lovely fun stuff divided by R2. And we can go ahead and plug and chug. That's my 9 volts minus 0.015 amps times 200. Oops, not 200. 100 ohms is where it goes there. All over 200 ohms. So my current is going to be 9.015 100 200 gives me 0.0375 amps. So now we've got the current going through our 200 ohm resistor of 0.0375 amps. We have I2, we have I3, and we are looking for I1. That goes ahead and gives us our last equation, and we can see the fact that my I1 is going to equal my I3 minus I2. However, you're going to notice when you plug your numbers in that something a little different happens. And you'll see that your current ends up being negative. Right. Nothing's wrong here. That just means that we actually made an incorrect prediction. We assumed that our current would be moving from our positive all the way around into our negative. That's not actually true. What we actually end up seeing is that our current is moving in this direction here. Right? That actually has a very specific reason. What's happening is that we are charging that smaller value battery. So we are using the 9-volt battery to charge the 1.5-volt battery. All right. So we've answered A, B, and C. That allows us to go back to D and E. And when we do that, we are looking at the fact that power is equal to current times voltage. Now notice we don't have the voltage that is being consumed by each of our resistors. We don't have the voltage for 100 ohms or the voltage for 200 ohms. And that's okay, because we also know that voltage is equal to current times resistance. We can actually take this equation and plug it in there. As a result, power is equal to current squared times resistance. Well, we have the currents and we have the resistances. So we can find the power for my R3 thing. So P for 3 is equal to my I3 squared times R3, which is 0.015 amps squared times 100 ohms. And it happens to be a number we've already seen before, which is at 0.0225. And power, as you should recall, is measured in watts. And now we're going to do the power for this one. So power for 2 is going to equal that, 0.0375 amps. That term is squared. Oops. Times my 200 ohms. Oops. Gives me a power of 0.28125 watts. All right, so this is 0.0225 watts, and this is 0.28125 watts. Now, you may notice that none of these are actually to correct sig figs. So if I were to go ahead and correct those for sig figs, those numbers do need to be pretty different than they currently are. We have 2 sig figs in this answer. If we take it out of sorry, we actually only have a maximum number of 1 sig fig in any of these particular answers. So when you do that, you're going to end up getting something that's very, very similar for all of them, because when you change this number for 1 sig fig, it ends up being 0.02 amps. And again, this one, when you change to 1 sig fig, is also 0.02 amps. This one ends up being a little bit different. It's 0.04 amps. And then we have 0.02 watts, and then 0.3 watts. So these are my answers with sig figs. All right, hope you learned something.